Hello, my name is Marcel Green, and I'm excited to welcome you to my final update presentation for the optimization of measurement and control parameters for extreme temperature mechanical testing systems. My work is under the advisement of Dr. Butler, Daniel Lewis, and Nicole Person. This project was made possible by the National Science Foundation. I'd like to provide some background for the vital importance of my research focus on limitations in available materials in high temperature testing in the context of technological superiority and national security. In my project, I explore miniaturized tensile testing to streamline the screening of advanced materials for extreme environments. The significance of this work lies in its potential to improve the efficiency of material selection and development processes, as well as being crucial for enhancing the resilience and performance of these systems in high temperature conditions. The focus on precise measurement and control during simulated operating conditions ensures reliable and accurate future mechanical testing outcomes. Actuation, measurement of load, and measurement of associated strain are key areas of research attention, as mastering these aspects will lead to better material characterization and selection. My research focus for tensile testing is split into three main sections. Actuation. In my research, we apply precise displacement to the materials during tensile testing. This allows us to observe how the samples respond to different levels of strain while also providing crucial insights into their mechanical behavior. Next, we have load measurement. By measuring voltage and converting it to stress based on sample dimensions, I'm able to obtain reliable data on the forces acting on the samples themselves. Lastly, we have strain measurement. My work also involves direct measurement of strain using advanced optical methods. This allows us to precisely quantify the deformation experienced by the materials under our different test conditions, offering a comprehensive visual understanding of the mechanical properties at play. The integration of these three aspects creates a comprehensive testing setup. This allows me to generate highly accurate stress strain curves, providing valuable information for material characterization. This is an image of the miniature tension tester in its original packaging when I first began. Version 1 of the miniature tension tester is my primary focus for this project, as it serves as the foundational platform upon which version 2 can be improved. By dedicating time and effort to optimizing version 1, I can ensure a stronger base. This can come in the form of rigorous testing and experimentation, as I was able to gain valuable insights in the system's performance and identify areas for future improvement. Version 1 provided me with room for innovative improvements, allowing for the fine-tuning and expansion of capabilities of that specific test platform. By addressing the limits and challenges faced in version 1, I'm able to pave the way for a more robust and advanced tailoring of version 2 for elevated temperature tensile testing. Instrument actuation enables precise control and manipulation of my experimental parameters, including the provision of power, associated control measures, data transmission and receipt, camera setup, and the conversion of rotational motion by the linear actuator. My analysis allowed me to study the effects of mechanical elements of the test system, leading to a deeper understanding of its interactions with materials and their behavior under various conditions. I built every component of the system by hand, including what's shown here for this initial setup configuration. This also includes the wiring for the data acquisition terminal and its differential pairs shown on the right-hand side. Multi-scale test frame configuration shown below was the main mechanism utilized for the testing process for my research. The components I'd like to focus on include the high-resolution load cell, which measures the force applied to the material sample during testing, providing precise data on the material's response to various forces and loads. Next is the servo motor, which actuates the movement and applies tension or compression to the material sample with controlled speed and force, ensuring consistent and repeatable testing conditions. Next is the rotary encoder, which provides real-time feedback on position and displacement. Lastly, we have the dog bone sample. The material sample's dog bone shape, highlighted in yellow, allows for controlled failure during testing, providing valuable data on the material's tensile strength and other mechanical properties. Working together, these components form a cohesive system for material testing. The servo motor actuates the crosshead's movement, applying tension or compression to the dog bone sample. As the sample undergoes deformation, the high-resolution load cell captures the resulting forces, while the rotary encoder provides real-time feedback on the sample's displacement. As you can see shown in this slide, these are the lab's tensile sample dimensions. The size of the dog bone sample I mentioned earlier is brought to your attention in the pictured comparison to a dime. Measuring strain for mechanical testing samples is essential for understanding material behavior, as well as determining strength and elasticity and making informed decisions in material selection and design for future high temperature applications. During my research, I initially began with the pre-existing software platform built by National Instruments called LabVIEW from 2018. I updated the software to 2023 and integrated our current test goals into the system. The previous version was simpler, however, mounting the device driver and establishing a baseline, I was able to develop a detailed simulated test configuration. Camera control and strain measurement. The implementation of the forward-looking infrared camera allowed for the tracking of sample movement and measurement of strain through optical methods. As shown here, I was able to set up the software for the desired acquisition modes to capture images at predetermined times in line with our testing goals. The timing of acquisition and programming of the camera was an important accomplishment in the strain measurement process, as well as the capture of the effect of the testing process on the material, as shown in the sample on the right-hand side. The repeated testing of the system demands a strict neutrality in location and original configuration. I built my own digital design for a frame to hold the system in place during repeated testing. My initial design evolved over time as the rotary cover needed to be compensated for the solidification of the system for balance. You can see the 3D printer on the right building out the initial design and associated rods. The mini tensile testing system was originally built with a 4-pin barrel connector for power that I was able to strip for implementation with an adjustable power supply to enhance user control of testing conditions. I soldered the ends and attached the appropriate leads and ground to this new power source. Perhaps the most exciting element of this project was the opportunity to allow the system to come to life. To build on the motor control that I had shown you previously through the power conversion, I built a switch that's shown here below that allowed for manual activation of the power supply before testing to allow for incremental control for test inputs. I was able to accomplish this, as you can see below, with the adjustable voltage applied after a test input had been pushed from the software to the switch, thus activating a controlled cycle from the user. As shown below, some of the challenges faced included the elimination of previous software, implementations to support repeated testing, as well as testing for the inclusion of the switch shown here on the right-hand side with the Arduino board and breadboard. I enjoyed all of these challenges as they pushed me towards a more direct programming input. This timeline provides a condensed picture of my project's development. After first familiarizing myself with material science tension testing and the physical components of version 1 in weeks 1 and 2, I moved towards the software control of the system through LabVIEW and the Spinnaker camera program. In weeks 5 to 6, by ascertaining the nuances and details of repeated testing and the combination between mechanical testing, material science quality assessment, and the project goal, I built enhancements to the system through my 3D printed frame design and remote power control switch configuration. From here, I advanced to the most difficult aspect of my project, which is currently in progress, which includes the development of a graphical user interface for data analysis that directly caters to desired user inputs. Lastly, I'm continuing to work on this while also integrating relevant data towards the improvements of version 2. The aspirations of my research are predicated upon enhanced automated data analysis. In material science, we first collect experimental data, and then we use automated or manual methods to analyze and understand the information gathered. Automated data analysis makes it faster and more accurate to extract stress strain data, helping us to understand how materials behave in real time during experiments. Automation can handle large amounts of data and find patterns, which allow the optimization of strength and fracture properties of materials, supporting faster material development and research validation. A special thank you to my audience, the ARL group,
as well as the National Science Foundation for making this possible.